Okay, so the first thing I want to talk about is the central limit theorem. Central limit theorem told us that if we had a population, large population, maybe a million people, and we measured some parameter that was normally distributed, I'm going to say, for instance, body temperature. The average body temperature might be 98.6 for this population of a million people. There's some variability within that population. That variability is described by the standard deviation. I'm going to say standard deviation in this case is 2 degrees Fahrenheit. Okay, and we know various things about that from the empirical rule that two standard deviations below the mean and two standard deviations above the mean would represent 95% of the population and so on. But the central limit theorem tells us a bit more. The central limit theorem tells us that if we take random samples from this population, say of size 100, and we take a random sample of 100 people from this population and we record what the average of that sample of 100 people is, and it comes out to be 98.5. For instance, if I do it again, I might get 98.7. If I do it again, I might get 99. If I do it again, I might get 98, so on and so forth. If I do that many times, well, I can create a new distribution of all these sample means of size 100, and that new distribution is going to approximate the mean of the population. Half of them are going to be below, half of them above. It's going to likely be normally distributed, and it's going to have the same mean. It's going to approximate the mean of the population as well. Okay. However, because these numbers, because by virtue of the fact that we're averaging 100 numbers, they're not going to be as spread out as the actual temperatures of the people in the population are. And this distribution, the sample distribution, is going to have a standard deviation. I'm going to call it SD for now. A standard deviation that's equal to the standard deviation of the population over the square root of the sample size. In this case, that would be 2 over square root of 100 is 10, or equals to 0.2, much narrower distribution. And now the same things that we knew about the population distribution and the empirical rule are true about this new distribution. In fact, interestingly enough, if this distribution is, say, skewed a bit, even though the population distribution is skewed, the sample, especially if you take a sample, a large sample, say large sample, say samples over size 30, even though the population distribution may be skewed, the distribution of the sample means, if you take repeated samples, turns out to be relatively normally distributed. So it evens that out into a normal distribution, even if there's some issues with the whether or not the population is normally distributed. Well, since we know that we have this relationship between the standard deviation of the population and the standard deviation of repeated samples from that population of the same size. Well, now we can take advantage of that. Okay, but before we do that, I keep calling this sigma the standard deviation. I call this the standard deviation also. Well, that's pretty confusing. So instead, I'm going to call this the standard error. Okay, so now the standard deviation of repeated samples is now going to be called the standard error. Okay, so now if I have this, if I know that 95% of the sample means are going to be within two standard deviations of the of the population mean, or what we think is the population mean. Well, if I take a new sample, if I take one sample of size 100, one single sample of size 100, well, I, I can say to myself, well, that sample could be exactly 98.6. It could be 98.7. It could be 99. It could be 98. But I'm 95% certain because of the empirical rule. I'm 95% certain that it's likely to be between two standard deviations below the standard error and two standard deviations above the standard error. Well, that gives us a lot of power now. Now we can say to ourselves, if I know what the standard error is and I take a sample, then if I add and subtract two standard errors from that sample, I can be 95% certain that the true population mean is between those two numbers, two standard deviations below and two standard deviations above the sample that I took, that single sample that I took. That's our calculation of the confidence interval. And as you guys know, two standard deviations below and above is really an approximation. If we look at this at that Z table, it's really 1.96 standard deviations for a 95% confidence interval, and it's 2.58 standard deviations to the left and the right for a 99% confidence interval. Gives us a wider interval, and it's 1.64 standard deviations below and above if we're satisfied with only being 90% confident that the true population mean is between two standard 1.64 standard deviation below and above the mean. Okay, so that's how we use that particular knowledge about the central limit theorem. That's how we justify doing these confidence intervals. Okay, good. I'm going to open up a new page now. Okay, I want to save that. And before I go, I'm going to do the same thing again now, except I'm going to move on to a little bit of a complication that we get into with this. So are we okay with that so far? Type into the chat box and give me some encouragement. Tell me that we're reasonably okay with that. Now, I'm not saying that you have to say you're going to be able to solve all the problems on it and stuff like that. We'll get to some problems after we get this preliminary introduction. Great. Okay, very good. Now one of the things that we mentioned here when we were doing this is that in order to find this 95% confidence interval, and now whenever I'm talking about 95% confidence interval, the same is going to be true for 99 and 90, except for the fact we're going to use a different number for adding the number of standard deviations, standard errors above and below. I've mentioned that in order to be 95% certain about this 1.96 standard errors above and below, well, I need to calculate the standard error. I need to know what the standard error is, in addition to whatever my mean for my sample is, right? So the problem here is that the standard error is equal to sigma over the square root of the sample size. Well, the sample size is I'm choosing, so I know what the sample size is. Now, sigma is the standard deviation, you may remember, is a parameter, right? It's a Greek letter, it's a parameter. It's the standard deviation of the entire population. Well, in reality, most of the time, for a couple of one or two homeworks, we assumed that we knew the standard deviation of the population, right? And that we didn't know the mean of the population, right? But in reality, just like we don't normally know the mean of the population and probably will never know it for certain, we also usually don't know the mean of the standard deviation, of the population. We also don't know that as well. Okay, so we're stuck. What do? We take a sample. Again, I'm going to take the same example. We take a sample of n equals 100 people, right? And it turns out that the mean for that sample turns out to be 98.4. I'm gonna assume I'm a little off here. I'll call it 98.5. Okay, the mean of that sample of 100 people. Okay, so now I'm going to say to myself, okay, now in order to calculate a confidence interval, I need to say, let's see, 95% confidence interval is going to be equal to x bar plus or minus the 1.96 times the standard error. Well, I need the standard error. So what is the standard error? Standard error is sigma, population standard deviation, of square root of n. Well, I know what n is, right? We decided that we know that, but I don't know what the standard deviation is of the population. Well, just like that sample of 100 people, this x bar, approximates the population standard deviation, well, the standard deviation, the spread of those 100 randomly chosen people, also approximates the population standard deviation sigma. So x bar approximates the mean, and the standard deviation of the sample approximates the standard deviation of the population. So instead of using sigma over the square root of n, I'm going to use the standard deviation of the sample over the square root of n, right? Well, I've just introduced a new layer of uncertainty here, right? Before, I assumed that I knew exactly what sigma is. So all this is premised on knowing what sigma is. Now I've introduced a new layer of uncertainty, right? And so now instead of doing this x bar plus or minus 1.96 times the standard error, well, now my standard error is really going to be my standard deviation over the square root of n for my sample, standard deviation of my sample over the square root of n. And because I've introduced that layer uncertainty, I need to make this confidence interval wider to make up for that lack of certainty, right? And we do that by choosing a different number than 1.96 for the number of standard deviations. We're going to go below and above the mean. And that number is determined by the sample size. Sometimes we refer to a sample size. Sometimes when we're referring to sample size, instead, what we wind up using is degrees of freedom. In this case, degrees of freedom, we're going to call it equal to n minus 1, right? So the deal here is the bigger the sample is, the more certain you are that the standard deviation is close of the sample is close to sigma. So we don't have to have that big an increase in 1.96. But if it's a small sample, we're going to have a big increase in 1.96. Okay, so instead of using the value 1.96, I instead now am going to use a different value based on the size of the sample that I'm getting my standard deviation from. Okay, and in order to look that up, like for instance in this case, the sample size is 100. In order to look that up, instead of going to a Z table, I'm going to go to a T table. I'm going to open one up right now. As a matter of fact, I think I have one posted. I had posted one for us to use on Blackboard for one or both of the homeworks. So I think, here we go. Here's a T table. Now, the real deal here is that, in fact, for every different sample size, you could create a table, a T table, that mimics the Z table. It could be 2 pages, just like the Z table that you use, that Agresti Z table that we've been using. So you would have a table for every sample size. Well, that's kind of cumbersome. So instead, what we do is we have a single table that gives us only the values that we really look for the most when we use a Z table or a T table. And that is a 90 for a 95% confidence interval, for a 90% confidence interval, and for a 99% confidence interval. So instead of having all the values that T could have, like we have in the Z table, you could have any value of Z, you could look up what probability you're working with. We're only going to be worried about using ones for 90, 95, and 99%. Okay, so, and in fact, if you look at this, there's a little column, there's a little row underneath here, right tail probability. It says for the T score for the area where the right tail probability is 2.5%. Well, that makes sense, right? 95% confidence means that it's the middle 95% of outcomes, right? So you have a right tail, 2.5%, and a left tail, 2.5%, adding up to 5% that's outside of this confidence range. That's the chances you're going to have an error. So that's why they put that in there that way. That's what that represents. Obviously, for a 90% confidence interval, it would be 5% on the left side and 5% on the outside. That's outside of that range of 90% confidence. Okay, so in our case, our sample size is 100. So we would go down to actually 99 because this doesn't use the sample size, uses degrees of freedom. So n minus 1 is 99, but closest thing is 100, so I'm going to stick with that. And the middle column here is a 95% confidence interval. So the value that we would use instead of 1.96 is 1.98. I'm going to round it off for our purposes today. I'm just going to use the 3 significant digits, 1.98. Notice that's very close to 1.96. That's because as the sample size gets larger, notice degrees of freedom, sample size 6 means 5 degrees of freedom, you would have to use 2.571 for 95% confidence. You would have to use 3.499, 3.5 for a 99% confidence interval. That's your critical value of T for that sample size. Notice that as the sample size gets larger, you're more confident that the standard deviation of your sample approximates the standard deviation sigma for the entire population. So the number you have to use, the t-value you have to use, goes lower and lower and lower until you get to a very large sample size, like over 100. Well, if it's an infinite size sample, if it's a whole population, it's 1.96. But once you get to a very high level, is once you get to past 30 or 40 or 50, you're very, very close to that 1.96 value as well. So a lot of times people will just abbreviate this. If they have a large sample size, say over 30, or I'd say over 40 or 50 or something like that, but certainly by 100, they might just use 1.96 as a convenience. Just for your information, SPSS never does that for its convenience. It always calculates the actual value of t, just like as if it had a table that had every value in it. So, for instance, if the sample size were 1,000, it might use 1.962, 1.96002 or something like that. Even though it's so close to 1.96, in real life you probably would have been happy to use 1.96. So when I go back here to work on this problem, right, instead of putting in the z value for 95% confidence, let me move this in my hand here. The z value for 95% confidence which would have been 1.96. Instead of using that, I use x bar plus or minus the z value for the sample size 100, which was 1.98, times the standard deviation for the sample. I'm going to say that the standard deviation for this sample was, let's stick with what I said before, 2 degrees Fahrenheit, right? 2 is 2 divided by the square root of 100, which is 10. It's going to be equal to 0.2 times 0.2, right? So my 95% confidence interval would be, in this case for our sample, the mean I got was 98.5 plus or minus 1.98 times 0.2. Okay, so that's 98.5 plus or minus, I'm going to work out that 1.98 times 2.2, 1.98 times 0.2, and that comes out to, I'm going to call that 0.4 degrees. Now I'm rounding here because I need to get through this quickly because we've got a lot of work to do tonight. Okay. All right, what happened here now? Oh, here I am. Okay. Plus 0.4, plus or minus 0.4. Okay, now you guys remember that this plus or minus, we have a name for that. We call that the margin of error. So if I add and subtract that, I'm going to have 98.1 to 98.9 degrees. I'm 95% confident that the true population mean, remember that might have been 98.6, the true population mean is between these two numbers. The mean that I found of my sample, right, of my sample of size 100 was 98.5. But I didn't have any understanding as to how likely it would be that that is close to or exactly the mean. But now at least I can say with 95% certainty that it's within this range. Okay, so I'll pause now. Are you guys comfortable with that? The idea of calculating the confidence interval, number one, and number two, substituting the t value for the z value based on the sample size when you're depending on the sample to give you the standard deviation of the population instead of knowing what sigma is. So let me see a couple of yeses and nos there. Is there a no in there somewhere? I think you can. I think you can respond anonymously. I think you can. I'm not positive, but I think that there's a way for you to respond anonymously if you can. See, it's really pretty. It's really fundamentally pretty simple, and and also pretty kind of intuitive when you really kind of like start to understand where this stuff came from. Okay, so now we're going to take this another step further. And that step that we're going to take next is this idea of hypothesis testing. It's nice to know that there's a range for when we take a sample, that there's a range that we have of level of certainty that we know that we understand the population mean to be within this range, but likely to be within this range. But how does that help us? Okay, well, let me give you an example right now how this might help us. Let's say that we know that people who have, let's see, what's a good way for me to do this? Um, 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 Let me think of a good example I can come up with. Okay, let's say I want to compare. Very frequently, we're comparing. We're doing interventions. We're comparing a drug to a placebo, so on and so forth. Let's say in this case, we want to compare the, uh, uh, the average the average blood pressure for people taking a drug versus the average for people blood pressure for people taking a placebo, right? This is for the drug, this is for the placebo, right? Well, in both cases, we're going to take well, instead of comparing to people taking a placebo, we're going to take the average blood pressure for everybody in a nursing home, so that we know if we go into a nursing home, we test everybody in that nursing home, and we know that the mean for everybody in the nursing home blood pressure is equal to 90, right? Well, now we go back and we sample only the people that are taking a specific drug. Okay, we randomly sample that group of people. Maybe there's several hundred people in this nursing home on a drug. Maybe we sample, I'm going to say we sample 25 people in this nursing home that are taking this drug. So we know X bar for this drug. We know X bar for this drug is equal to 80. Their blood pressure is equal to 80. Okay, so I may know the mean for, let's say I know the mean for all the people in the nursing home, right? Let's say I also know the standard deviation for all of the people in a nursing home, and I happen to know that it's equal to 10. Okay, so I might say to myself, okay, I take a sample, sample of size 25, I get an average of 80, and I want to compare it to a known population that has a mean of 90 and a standard deviation of 10. Okay, known standard deviation of 10. Okay, so I might say to myself, okay, I know the standard deviation, so let's see what I can do with this. Let's see, I can say, well, let's see how certain I am that of what the mean is, the population mean is for the people taking the drug, given I've only sampled 25 of them. So I need a confidence interval. I know mu here, but I only know X bar here. So let me see what I can come up with in terms of a confidence interval. So let's say X bar plus or minus. In this case, I'm going to use sigma. I'm going to assume that the standard deviation of both these groups is the same. I'm going to use sigma, so I know I can use the z-score, right, which is 1.96 for alpha is equal to 0.05 or 0.05 chance of being wrong, or 95% confidence. Z-score for 0.05 times the standard error. Okay, so it's going to be X bar plus or minus 1.96 times the standard error, which is equal to 10 sigma over the square root of the sample size, square root of 25. Okay, so I'm using 1.96 because I'm assuming I know the standard deviation of the population. Okay, so now I can say X bar plus or minus 1.96 times 10 over 5, which is equal to 2. So I can say that the 95% confidence interval for the true population mean of this group is equal to, let's see, what is it equal to? It's going to be equal to 4 less than 80, 76, to 4 more than 80, say 84. So I'm 95% certain that the true mean for this group, where I only had a sample to work with, but I knew the population standard deviation, right, is between 76 and 84. But I know that whoops, is equal to, is equal to 90. I know this mean is equal to 90. This one, I only know that its mean is likely to be 95% certain between these two numbers. Well, the fact that this mean, known mean for this group, is outside of the confidence interval tells me that not only am I 95% sure that this mean is between these two numbers, but I'm also 95% sure that this mean is different than this mean, that this group has a lower blood pressure than this group has. So, in essence, I have a way of proving, at least proving in the sense to a certain level of certainty, 95% certainty in this case, that there's a difference in the mean of this group and this group, given that I know one of the means for sure, and that I know, and for the other group, I only know the sample mean and the sample size. Assuming that I know the standard deviation, or I assume the standard deviation is the same for both. Okay, so that's basically how I would try and prove that there's a difference between these two at a certain level of certainty. If I wanted a higher level of certainty, like 99%, I would have used 2.58 here. Now, I'm going to complicate. I see there's a couple of comments on, but I'll get to them in a second. I'm going to complicate this now. And I'm going to say to you, suppose I don't know what the standard deviation is for these two groups. All I know is that the mean of the entire population, of this entire population, is 90. And this population, I only know that the standard deviation is equal to 10. Right? And I say to myself, well, I don't know the mean, but the mean of the sample was 80. I don't know the population standard deviation, but the standard deviation of the sample of size 25 was equal to 10. So that's really all I can use. So instead of saying x bar plus or minus z, I'm going to use the t-score for that specific sample size times the standard error, right? Times the standard error. Okay, so again, doing exactly the same thing, 80 plus or minus. Well, now what's the t-score going to be for a sample size of 25? Well, we go to our table. Okay, for a sample size of 25, that's 24 degrees of freedom. The t-score is going to be 2.064. So I'm going to go back here. You saw how I got that right. Sample size of 24, the 95% confidence interval column, 2.064. So this is going to be 2.064, 2.064, up 2.06. Did I pick the wrong one? Let me go back. Somebody, let's see, 24. No, it's remember, this is degrees of freedom, right? Remember, column is degrees of freedom, not sample size. And degrees of freedom are equal to the sample size minus 1. So that would make it 2.064, that one over there. Okay, I'm going to use 2.06 probably anyway, just so I don't slow this whole thing down. 2.064 times the standard error. Now, what's the standard error equal to? Well, the standard deviation of the sample, which is 10, over the square root of the sample size. So that hasn't changed. So the square root of 25. So that's going to be 80 plus or minus 2.064 times 2. Right? The only thing's changed here now is we're using the z-score instead of the t-score. So let's see what that comes out to be. Okay, so our margin of error is going to be equal to 2.064 times 2 times 0.28. Was it 2? Yeah, times 2, which is 4.1. I'm going to call it 4.13. Right? So 4.13, our margin of error is 4.13. So 80 less 4.13 is going to be 75. 875.87 to 84.13, right? So our confidence interval now is a little wider than it was before, right? Why is it wider? Because we had to depend, we're compensating for the fact that we don't know what sigma is, the true population standard deviation, And we had to use the sample standard deviation, which introduced that level of uncertainty. This z-score is going to be bigger and bigger as the sample size gets smaller. As the sample size goes down, right? As the sample size goes down, our t-value goes up, making this a wider interval, right? Making up for that extra uncertainty. Okay, so let me pause for a second. How do you guys feel about that? Okay, you guys okay with that? I'm going to back up. I just want to make sure you're okay with what I just did, and I'll back up and take a look at the questions that are above on the on there. Okay, good. Let me back up here and see what these questions were. Okay. However, on assignment 3B, question 11, 12, there is no mean provided. I think that's actually because it was based on the one before, but I'm going to open up 3B and take a look at it right now. There are a couple of errors on the assignments, but he looks at, I do go back and look at the errors if I can. Right. Okay. X bar. Yeah. Okay. I'm going to open up that homework and see if I can find what the problem is there. I'm not sure about the Arizona assignment. I think they're right. Right. I'll check. I'm going to check on it right now. So I'll start with, okay, so let me go back to my list of issues that came up. Okay, now actually I want to do one more thing. I just want to show you one more thing before I go to these problems. And that is this idea of hypothesis testing. Okay, because this is important because this is going to come up from now on. We're going to be phrasing our solutions to problems this way from now on, at least in most cases anyway. So, in many cases, what I'm trying to prove is that I have two populations. I have people that have two populations. Okay, I have people that are taking a drug versus people who are taking a placebo. People who have an exposure like smokers versus non-smokers, right? People who have been exposed to asbestos versus people who are not exposed to asbestos, and so on and so forth. So very frequently I'm going to have two groups. I want to compare those two groups. Now, when I'm working with a numerical variable, okay. Now I'm gonna pick one out now. Instead, I'm going to say blood lead level now. Blood lead level. Okay, so for children, I think that the action level nowadays is 5 parts per billion. Five, oh no, excuse me, not 5 parts per billion. 5 micrograms per deciliter of blood. Okay, that's the action level nowadays. Okay, so let's say I want to compare. I want to compare a population, and I want to compare them to the action level for the for blood lead levels, CDC's action level for blood lead levels for children. Okay, so I'm going to be comparing now. Let's say let's say I want to look at children in the Bronx in housing that's more than 30 years old. Okay, now there may be 500,000 units, apartment units in the Bronx. Maybe not that many. Say 200,000. 200,000 apartment units in the Bronx that are greater than 30 years old. Back in the periods when they were possibly were using lead paint, right? So I'm interested in knowing whether the average blood lead level of children in the Bronx exceeds 5 micrograms per deciliter. So this is the number I'm interested in. I want to. That's the average. That's my mu is 5. I want to know if I exceed that average. That's a set number that I'm comparing it to. Okay, so I want to see. I want to do a study where I sample children from the Bronx randomly, and I want to see if I exceed that level or not. Okay, so let's say I only have funding to do a sample size of let's say 64. Okay, sample size is 64, not a very big sample, right? But I have funding for sample size of 64. I randomly sample that number of children in the Bronx, and I come up with a sample size, and I come up with a mean blood lead level in those 64 children, equal to, let's say, 3.9, right? So now I say to myself, okay, now I want to compare these two numbers. Well, I could say to myself, let me do a confidence interval for 3.9. Given that, it's a small sample, I'll use the t-value because I don't know what sigma is. I'll use the t-value. If I know, let's say I know that the standard deviation of this sample was equal to 2.1, right? So a big variable, maybe not quite that. Let's say 1.5. Right? Variability was 1.5 in this sample, pretty variable. But I don't know what sigma is. Sigma is unknown to me for this population in the Bronx, and mu is unknown to me for this population in the Bronx. Otherwise, I wouldn't bother doing it. I would know if it's above 5, right? So I say to myself, maybe I can do a confidence interval for this and see if the confidence interval overlaps 5 or not, could possibly be above 5 or not. Well, there's a better way to do this, right? And that better way is to actually calculate what the probability is that you would have a value. This, if we took a sample from a population that had a mean of 5 of size 64, what's the probability that we would get a result as low as 3.9? Is that likely to happen? Well, we can actually calculate that. The way we're going to calculate that is we're actually going to calculate a t-score or a z-score for this value. I'm going to calculate a t-score, for instance. Okay, and that t-value, that's t represents, just like z, t represents the number of standard deviations apart, or standard errors apart. Two values are, one for a known population, one for a sample from a population, right? So really 1.96, 2.58, they were numbers of standard deviations apart that you needed to justify your confidence. So I'm going to do the same thing here. I'm going to say my t-value, the number of standard deviations apart that these two means are. Well, what are they? It's x bar minus mu, right? Those are the difference between the two means, right? So that's 3.9 minus 5. That's how different they are over the standard error. That's our standard deviation. That's our standard deviation for repeated samples of size 64. It's called our standard error, right? So let's calculate this. So my relative t-score, number of standard deviations apart, is going to be equal to x bar 3.9 minus 5 over the standard error. Now I got to calculate my standard error. My standard error is equal to sigma. I don't know that. I have to use 1.5 over the square root of my sample size, which is 64. Okay, so I'm going to calculate this. This is going to be 8. I'm going to call this 1.6, making it come out an even number, right? Square root of 64, so that's going to be equal to 1.6 over 8 is going to be equal to 0.2. Am I right about that? I think I'm right about that. Yes, I am right about that. It's equal to 0.2, right? So it's 3.9 minus 5 is equal over 0.2. That's my standard error. That's going to be equal to negative 1.1 over 0.2, which is going to be equal to, let's see, it's roughly, I'm just going to call it roughly 5. Okay, my t-score, these two numbers are 5 standard errors apart. Well, if I go back to my z-table, how far apart do I have to be to say to myself that these things are, I'm 95% sure that these things are different? Well, for a sample size of 64, okay, I'm going to call it, I'll be conservative, call it 60. They have to be 2 standard deviations apart. My t-score has to be 2 standard deviations, right, in order to be 95% certain that these two things are different. Okay, so my t-score that I have to be apart is 2. That's called my critical value of 2. If the t-score I calculate is bigger than that critical value of 2 that I need for sample size of 60 or 64 in this case, then I can say with 95% certainty that they really are different, right? So let's see, what did I get? What I got was my critical value of C was 2. What I actually got was Let me click back in here. Okay, what I actually got was 5. So this number is greater than my critical value of t. So I can say that I'm 95% certain that the children in the Bronx have a blood lead level, an average blood lead level overall, if I tested everybody in the Bronx, of less than 5. I'm 95% sure that that's true. Okay, so that's interesting, right? So the thing here is that we're not going to phrase it that way. I'm going to do the same problem. All I'm going to do is change the phrasing on it. I'm going to start out by suggesting a hypothesis, and then we're going to test to see if that hypothesis is true. Okay, I'm going to say to myself, let's see. I know that I want to know if the blood lead level for children in the Bronx, right? If I want to know if that is equal to 5, right? So what I want to know is if the mean blood lead level in children in the Bronx is equal to 5, right? So I'm going to start off with a hypothesis. I'm going to start off with the hypothesis that indeed I want to know if it's not equal to 5. I want to know if it's less than or greater than 5. If it's different. That's really what I want to know. I want to prove that it's different than 5. Okay, it's greater than 5, less than 5. I want to know what the relationship is. So I'm going to start off with the idea that, let's start off and say that it's equal to 5, that we don't have any evidence to say that it's not. And we're interested in proving that the mean blood lead level is not equal to 5. It's either greater than or less than 5. We're going to call this starting point, we're going to call that the null hypothesis, meaning no difference, right? Null meaning no difference. The null hypothesis. Sometimes you'll see it also as, abbreviated as H with an O with a slash through it, something like that. Null hypothesis. That's our null hypothesis. That's our starting point. And we want to see if we can't prove our alternative hypothesis, right? Alternative hypothesis, which is that there is a difference between the value that we're testing it against, 5, and what the mean for the Bronx is, which we really don't know because we took a sample, right? So that's our alternative hypothesis. And the idea here is we want to prove with 95% certainty, we want to say that we can reject this idea and accept this idea instead, that it's different, larger or greater, right? So we want to be 95% certain. Well, another way of saying 95% certainty is saying that we want less than a 5% chance of being wrong. Now, in the videos and so on and so forth, you may remember that we've referred to certain kinds of error as alpha errors, right? Those are the important kinds of errors, alpha errors, right? So we're going to call that less than 5% chance of being wrong. We're going to call that our alpha error. We want our alpha to be less than 5%, right? We're going to test it to that level. That's the same as saying 95% certain, right? Our alpha is 5%, 95% certain, same thing. And we're going to do exactly what we did before. X bar minus mu over the standard error is equal to our t-score, our t-value, right? Because it's only a sample size. It was only a sample size of 64, right? Except this time, I'm going to say to myself, okay, I'm going to say to myself, I forget what I said before. I'm going to say X bar is equal to 4.8 in this case, right? So let's see what happens now. Okay, so over our standard error, right? So X bar was 4.8 minus 5 over our standard error. What's our standard error equal to? Our standard error is equal to our standard deviation. I think I said it was 1.6. That's equal to 1.6 over square root of 64, which is 8. 8 into that is 0.2, right? So our standard error is equal to 0.2. So our t-score is equal to -1. That's our t-score. What did we say our t-critical had to be? How far apart did these two values have to be in terms of the number of standard deviations? I think we said that our t-critical was equal to 2.00, right? It was equal to 2. Now, these are not far apart. Our t-value is only -1. So they're not far apart for us to say with 95% certainty, less than 5% chance of being wrong, that these two values, 4.8 for our sample and 5 for our known value, we can't say with 95% certainty, less than 5% chance of being wrong, that they really are different. So what happened in this case? Where before the previous problem, we rejected the null hypothesis and accepted the alternative that they're different, now we fail to reject the null hypothesis. We don't say this is true. We only say we failed to reject the null hypothesis. We didn't have enough evidence to prove that the average blood pressure, or the average blood level of children in the Bronx is different than the national action level. Okay, that's how we use this. That's hypothesis testing. On Tuesday, when you get new material, you're going to see another version of this, where instead of this is called a single sample t-test. Why is it called a single sample t-test? Because in this case, you're comparing the x bar, the mean from a sample, to a known value. That known value of 5 could be a known mean for a population, or it could be a set value like a standard or something like that, but there's only one sample involved. As we move forward, you're going to see that we're also going to work on situations where you have two samples. For instance, where you might take people and test a blood pressure medication, and you take the average person that took the drug versus the average blood pressure. Maybe you don't know you take a sample of people who you give a placebo to, and you look. You can take the average for the people who took the didn't take the blood pressure medication, and you're going to compare the two of those to see if you can be 95% certain that the drug was different, gave you an average blood pressure that was different than the placebo did. And in that case, your formula for T is going to be equal to, in that case, you have two samples. So you're trying to prove that the mean of group 1 minus the mean of group 2 over the standard error for those two groups, the standard error for the distribution, the spread of the distribution, right? Except in this case, you're using x bar 1 and x bar 2 because you don't know either mean. You only know sample means. And you're testing those two. And in those two, your null hypothesis would be the mean of group A is equal to the mean of group B, or the alternative, the mean of group A is not equal to the mean of group B, right? That means you know an alternative hypothesis. Okay, so and that's the way we do that. But I'm jumping ahead there. That's something that we're going to start to cover on Tuesday. For now, we're working with just this material, and we'll worry about that as we move on. Okay, so guys, how do we stand now? Are we okay on that? I know that we gradually made this. Each step made this just a little bit more complicated, but I'm hoping I stepped through it slowly enough and deliberately enough that you could see the progression here. That there's an order here to these things. We're building from one to the other. Okay, for right now, for tonight, we're just happy to get up to the point where we know how to do that single sample t-test, where we compare the difference in the one mean versus the set number over the standard error, and see if that's different than the if that number, that t-value, comes out bigger than the critical value. So how about that? Are we okay? And then I'll go on to these problems. Okay, everybody still awake out there? Okay, good. I hope so. All right. So now let's go on to the problems. Okay. And I'm going to start with somebody just threw one up there. Let's see. There's a couple: 4, 12 through 14. I think I might have that listed already. 3B, 11 and 12. Okay, let's start with 3. 3B, 11 and 12. 11 and 12. And 4, what was that? 4, 12 through 14. 4, problem 4. That's one's assignment there. Okay, let me add that one. for assignment 4, 12 through 14. Okay, let's start with 3. Let me move this out of the way. See which homework this is. 3B. Okay, is that the right one? Or is that the one that came up here? I think so. Whoops. 3B, 4, 5, and 6, and 11, and 12. Oh, I need to blow this up. Okay, let's see if we can get this big enough to actually read. 3B, first was 4, 5, and 6. Let's take a look at 4, 5, and 6. 4, 5, and 6. What proportion of the means of the samples of size 20 are expected to be larger than 33 milligrams per 100 liters? Okay, this one actually builds up from a couple of steps back here. Okay, let me blow this up a little bit more. Oops. My goodness, what I did there. Oops, that's the wrong one. Where'd it go? Did I lose it? I lost track of it. Here it go. Here's 4. It's been recent. It disappeared on me. Tell you what, I'm going to open up Blackboard. I think it's going to be easier to read on Blackboard anyway. Okay, let's do number 3B. Okay, let's see what we got here. I think it was 11 and 12. Oh, no, we had another one before that, right? 4, 5, and 6. Okay, let's take a look at 4, 5, and 6. Let's see. Among adults in the United States, the distribution of albumin levels, type of protein, blah, blah, blah. The mean is 29.5, and the standard deviation, we know the entire population here, right? It's 29.5 is the mean for the population, and standard deviation for the population is 9.25. Suppose you select many random repeating samples of size 20 from the population and calculate the mean for each sample. What would you expect the mean of the sample means to be? Well, you would expect that to mimic the population mean, right? What would you expect the standard deviation be for the repeated samples and the means? Well, that gets a little more complicated, right? Because that's going to depend on the sample size. So you would expect the standard deviation for the repeated samples of size 20 to be sigma 9.25 divided by the square root of 20, whatever that comes out to. Another name for the standard deviations is, of course, the standard error. Okay, question 4. The proportion of means of the samples of size 20 that are expected to be larger than 33 milligrams per 100 milliliters. Well, for starters, we would expect the average of the sample means, right? We're talking about the sample means here now, right? The average of the sample means to be the same as the population, 29.5. But we would expect the standard deviation, in other words, the standard error of the sample means, to be equal to 9.25 divided by the square root of 20. Okay, so I'm thinking the square root of 20 is probably, let's see, about a little under 5, I guess, right? About 4.5. 4.5 and 9.25 is about 2. So I'm thinking it's about 2. So how different is 33 from 29.5? How many standard deviations? Well, 29 versus 33, that's about 3.5 divided by the standard error, which was 4.5, which comes out to about positive, let's see, it comes out to a plus 0.8 or something like that. So a z-score, remember we're using z here because we know the population standard deviation. Z-score plus zero point 0.8, you could look it up on the z-table. You would find that since it's to the right of the mean, the area that's represented by a z-score of zero point 0.8 is going to be, let's say, 75% of the distribution, 0.75. But this is looking for the percentage that are higher than 33. So you would subtract 0.75 from 1 and wind up with a figure of about 0.25. What about a portion less than 28? We'll use 28 minus 29.5, be 1.5, divide by the standard error, which was 2, what was it, 2 or something like that? Divide by that, get a z-score, and then look up on the table that negative z-score, which is going to be to the left of the mean, because for 28, to the left of the mean. So that area to the left of that is just going to be read right off the z-table. Okay, so, and 5, the sample mean is expected to be between the two of them. Well, you could just, if you sketch it out, you'll see that if one is 75% of the mean, and then like the other part, this one from here down is 75%, and from here down is 25%, then it leaves 50% in between them. You know, it's just basically like slicing up a pie. So I don't want to spend too much time on that because I think 11 and 12 probably be a little bit more challenging because they came up. Okay, probability of being born, of an infant being born prematurely in Mexico is 0.15. What is the standard deviation for the proportion of premature births for repeated samples from the population of size 25? In other words, if the true proportion is 0.15, 15% of children are born prematurely, and you took a sample of size 25, well, the first time you take the sample, you might get 0.14, 14 out of 100, let's say, or whatever that similar numbers out of 25. Or you might get 16%, or you might get 20% or 10%, right? But overall, if you repeat it often enough, the average of the repeated samples is going to be 0.15. But now you want to know what's the variability of those repeated samples. The 0.16, 0.14, 0.21, 0.14, so on and so forth. What's the standard error? What's the standard error, the standard deviation of those repeated samples? Well, that's equal to the square root of p, which is 0.15, times 1 minus p, which is 0.85, over n, over the 25, and then you work all of that out and then take the square root of it. And the real trick here is being careful to work that out in the right order before you actually do the calculation. Okay, so do you need me to do the calculation there? Should I do the calculation? Okay, let me do it. So let's see, 0.15 times 0.85 is equal to 0.1275, right? That's p times 1 minus p. I'm going to divide by the sample size, which is 25. That's equal to this. And then I'm going to take the square root. That's everything that's under the square root. Now I'm going to take the square root of that, and it comes out to about 7.1%, 0.071. Okay, guys, okay with that? Make sense? Is that a yes? No? Are we stunned? Okay, so at least one yes. Let's take a look at the second part. As in the example above, now I added those words because I meant to use I assumed that you would know to use the same percentage, but actually that's kind of not really that clear, I guess, looking back at it. So I added in as in the example above, probability is 0.15. We would expect 95% of the proportions of size n equals 625 to be between this and this. This is a confidence interval problem, and it works just like confidence intervals for a regular mean for confidence. Doing this for a excuse me, doing this for a proportions where the point measurement, the point value, instead of being a mean, is equal to a proportion, right? We never know what p is. The true, well, in this case, we know it's 0.15, but in reality, we really never know what it is. But we know, for instance, that if it is 0.15, we kind of know something about the way that it's distributed. We know that the standard error, the spread of all the different values that you might like to have, is going to be equal to, the square root of p times 1 minus p over n. So that standard error in this case, as before, is going to be a little bit different because different sample size. By the way, I hope you notice it was a different sample size. Maybe that's some of the confusion also. 0.15 times 0.85 over 625. Okay, get my calculator back. And clear. 0.15 times 0.85 equals this, divided by 625 equals this, and I'm going to take the square root of that. Okay, so it's equal to 0.0143. Is equal to 0.0143. So now what is my confidence interval equal to? It's equal to p cap, p, plus or minus. Well, since I know, since I almost always assume, because we use large samples, the sample is very large, right? Since the sample is very large, I use the z-score here. Z times the standard error. So P plus or minus P or P cap plus or minus 1.96. The proportions we're almost always going to be using the Z value because we're only going to do it for large samples, times the standard error, which is equal to 0.0143, which we just calculated. So it's going to be equal to 0.15 plus or minus, and I'm just going to call that 2 times that is going to be 0.028. I'm going to call it 0.028. Right, 0.028. So our 95% confidence interval is going to be equal to 0.122 to 0.178, I think. Did I do that right? 0.0. No, hang on a second. I didn't do that right. That's 0.02. That's 1.15, 149.7 roughly to 9. Let me do this. I'm losing track here. I'm getting tired as the evening's going on here, and I'm getting careless. Let me just do this. Okay, let's see. 0.15 minus 0.028 is equal to 0.122. I had it right the first time, I guess. Right, and so on and so forth. Did I subtract 0.02? Yes, I did. Okay. Right, and 0.148. I think I had it right the first time. Let me go back to the chat box and see if you guys are okay with that. Are you guys okay with that? Yes. Good. I like yeses. Yeses are good. Except I feel a little uncomfortable. I'm not getting any no's. I want to see a no every once in a while, you know? So, okay. So, and then you calculate the upper and lower level. So let me go on to the next problem. The next problem that came up was, let me go to this text edit thing here and see what came up. Okay, 4, 5, 6. So assignment, somebody just mentioned assignment 4 over here in the chat box, right? Let me go back. Z's. I see a couple of Z's there. I hope that's the Z table you're referring to, not sleep. For assignment 4. Okay, let me see assignment 4. Okay, what number was that again? That was assignment 4, 12 through 14. Okay. Down towards the bottom. Okay, 12 through 14. Okay, let me make that a little bit bigger. Based on a careful study of Night of the Living Dead zombie, it appears that, this is a proportion also. Zombies are predominantly male. A random sample of 100 zombies from Zombie Movie Marathons found that 58 of the sample were male. In other words, 58 were male, 42 were female. So the proportion of male zombies was 0.58, 58%. Okay, so what is the point value for the proportion of male zombies? It's 0.58, right? 58 out of 100. Okay, so the next question is, what is the margin of error for the confidence interval for male zombies? I separated this out. I think it confused a couple of people. The margin of error is the part that you add and subtract to your point value, to your mean, or to your proportion, like 0.58 in this case, which would be, again, because it's a big sample, right? Greater than 30, greater than 15 on each side, or 30. Okay, margin of error is equal to 1.96 times the standard error. And the standard error is calculated by the square root of p times, which is 0.58 times 1 minus p, 0.42, over the sample size, resolve all that, and so on and so forth. So, and then I asked you for the 95% confidence interval. So let's do that right now. Let's actually do that problem. Okay, let me get a piece of paper back up here. Okay, so the p cap, the proportion, I don't know the true pop. I didn't look at every zombie movie. I feel like I did, but I'm sure I haven't. P cap is equal to 0.58, right? And the standard error for repeated samples, if we took repeated samples from a population like that, the standard error would be equal to the square root of p times 1 minus p over the sample size. Well, our sample size here was 100. We sampled 100 zombies from these movies. So the standard error is equal to the square root. We use, instead of p, we use p cap because that's all we have. 0.58 times 0.42 over 100. Okay, and okay, so that's going to be equal to, helps to use a memory calculator here, because then you don't have to copy things over and over again. It even helps more to use Excel, to tell you the truth. Okay, 0.58 times 0.42 is equal to this, divided by 100. Right, we resolve all of that before we take the square root. Now take the square root of that result, and it's about 5%. It's 0.049, right? 4.9%. Okay, so I'm going to write that in there. It's going to be equal to 0.049. So now I'll set up my confidence interval. P cap plus or minus, I use 1.96 because when we're working with proportions, we only work with large sample sizes. So we're going to use the z-score instead of the t-score, right? Times my standard error, which is 0.049, okay, which is about 5% actually. Okay, so what do I wind up with here? I wind up with 0.58 plus or minus, and I'm going to go back here, clear, and I'll clear memory also. Let's see, 1.96 times 0.049 is equal to 0.09. I'm going to put that into memory. I'm going to add and subtract that from 0.58. 0.58 minus my margin of error is equal to 0.48. I'm going to just remember that, 0.48. And on that 0.58 plus my margin of error is equal to 0.67. So my 95% confidence interval is going to be 0.48 to I don't remember what it was, 0.67. I'm going to call it for our purposes right now. That's my 95% confidence interval. Can I say 95 with 95% certainty that it's not 50-50? That it can't be, that it's not likely to be 50-50? No, I can't really say that, can I? Because it could be 50%, because that's inside of my confidence interval. I can't be 95% sure that it's not. Had our confidence interval come out to be 0.52 to 0.69, right, I could have said with 95% certainty that, I'm 95% sure it's not 0.5. Why do I say that? Because I'm 95% sure it's above 0.52 and lower than 0.69. So the true population proportion, I'm 95% sure, is not this. The better way to do this is the t-test. And on the t-test, you would have said 0.58 minus 0.50 over the standard error, which is 0.049. Come out a t-value and look to see if that t-value was greater than the critical value of t, which when you use the z-score is 1.96, right? For a large sample size, or for, if you know the population standard deviation. Okay, and let me go. Okay, so some of you brought up an assignment 5, numbers 7, 8, 9. I think also there was another question about assignment 5. Let me just get back to see if that's the same thing. Assignment 5, 7, 8, 13, and 15. Assignment 5, 12, about basically everything after 7 on, after problem 7 on assignment 5. Let's take a look at that. Okay, let's take a look at assignment 5 now. Let me get to it. Okay, assignment 5. Take a look at question number 7. Okay. I can't read it. What is it? Let me do it online. Yeah, it's like I said, it's probably easier for me to actually just go online and do it from. Did I close it? Yeah, I did. Crap. Oh, excuse me. That's a engineering term. You don't use it in statistics. Okay, let me get back to that. Oops, that didn't work out. Oh, I don't want this one. I want my automatic log on, which I got on FoxPro. Oh, there it is. It's still there. Okay, leave page. Oh, I didn't mean leave the entire thing. Okay. It remembered me? Let's go to assignment 5. Okay, single sample hypothesis testing. Actually, we kind of almost covered that already, right? Because we got into that tonight, but let's see what we got here. Okay, question 7. Okay, let me blow this up a little. Maybe, yeah, there we go. Okay, question 7. Which one was the first one? 7, I think it was, right? Given the season playoffs, what is the t-value associated with the difference between regular season and let's see, rejecting our hypothesis? 10, 11, 13. Okay, I got it. Let's go back here. You want to test whether there's a number of fouls called in regular season games is different than during the NCAA tournament. You happen to know, or somebody keeps statistics on this, the mean number of fouls called during all regular season games is 40.1. You know that that's the case. You know that it's 40.1 because you know the mean. Somebody tabulated that for every game. Now, you don't have time to do the statistics for the playoff games, but you were able to watch and record 16 of the playoff games, like in hockey and basketball, and it seems like getting to be almost every sport except maybe football. The playoff season is longer than the regular season. You have playoffs that comes playoffs upon playoffs, right? So at any rate, but you can't watch all the playoff games. You only watch 16 of them randomly selected. So excuse the opinion. Okay, during 16 regularly selected playoff games, randomly selected playoff games, n equals 16. The mean number of fouls is 38.1, and the standard deviation is 5.8. Well, what's happening here? We have a set number, and we want to predict whether the mean mu for postseason play is the same as mu for regular season play. For one of them, we know mu. For the other one, we only have a sample. So this is a single sample t-test. And, before I go any further, I'm going to write this down as a hypothesis. Might as well learn how to do this now, right? because we're going to be doing this a lot in the future. Well, not for you guys, because between me and you, our semesters, it's like a couple of weeks away from over already. It's brutal. It's brutal. Okay, so how would I expect this? How would I describe this? I know that mu for the regular season is equal to 40.1. I don't know what mu for the playoff season is. I don't know what that is, but I do know that x bar for the playoff season is equal to what was it? Uh, is equal to 38.1 with a standard deviation of 5.8. 38.1 is equal to 38.1 with a standard deviation of 5.8. Right? So I want to know whether mu for the regular season is equal to mu for the playoff season. Right? Well, I'm going to set up a hypothesis test. And my null hypothesis is going to be, okay, my null hypothesis is going to be that mu for the playoff season is equal to mu for the regular season. Now, I know mu for the regular season, so instead of putting in here mu for the regular season, which I could do if I wanted to, I'm just going to put in 40.1. So is mu for the playoff season equal to 40.1, right? Or are they different? Okay, so my alternative hypothesis is going to be that mu for the playoff season is not equal to the same average as mu for the regular season. I'm going to add one more thing. I'm going to say most of the time, if I don't say so, my alpha, my acceptable level of error is equal to 0.05, right? My alpha is equal to 0.05. Alpha error is equal to 0.05, or 95% certainty, another way of saying it. So I need to compare these two. So how do I do that? Well, I'm going to do a t-test, right? It's a single sample t-test. I want to see if my t-value for this sample size, our sample size is 16, of course. For this sample size, if my two values, if my two means are far enough apart that they're going to be more than this number, critical value of standard errors apart for me to be able to reject the null hypothesis. So let's see what my t-score is going to be. It's going to be equal to 40.1. It's going to be equal to x bar minus mu, because it's a single sample. I don't know mu here, over my standard error. And my standard error is going to be equal to sigma, but I don't know sigma, so I'm going to use standard deviation. 5.8 over the square root of my sample size, which is 4. So that's going to be equal to 1.4 into 18, 1.4 and 2, 1.45, right? So that's what that's equal to. Right, so it's going to be equal to x bar. Let's see what that comes out to. X bar is 38.1 minus mu, which is 40.1, the known value, over my standard error, which is 1.45. So my t-score, the number of standard errors apart that these two values are, and I'm using t because it's a small sample, it's going to be equal to 0.9 and 0.1 is going to be equal to 40.30 is equal to 2 over 1.45. Okay, so 2 over 1.45. You guys will tell me if I'm doing this wrong, right? If I make a math error, right? I hope. Divided by 1.45 is equal to 1.38. My t-score is equal to 1.38. Now, is that a big enough difference for me to say with 95% certainty that these two are different? I can reject the null hypothesis or accept the old. So the key to that is, does it exceed my critical value of t? And my critical value of t for a sample size of 16, or in other words, 15 degrees of freedom, my critical value t is 2.13, right? So 2.13, does it exceed 2.13? No, it doesn't exceed 2.13. So in this case, I fail to reject my null hypothesis. I don't say I accept it. I just say I fail to reject it. I fail to prove that with less than 5% chance of being wrong, even though it looks like it, because there were fewer fouls called, even though it looks like it, I failed to prove that with the level of certainty that I assigned that I wanted for myself. So I fail to reject the null hypothesis. Okay, let me go back to this homework, go a little further. Okay, that you can see your regular C. In this case, I didn't bother to put the 4.5. You just use regular season versus playoffs and so on. Okay, okay, let's see. What is a t-value associated? I think we answered that. Okay, the average forced expiratory volume, question 9. Average FEV, forced expiratory volume, that's the amount of air you can expel in 1 second, I think it is, volume. For adult males, for normal adult males, 40 is known to be 3 liters. You randomly sample 60 male construction workers exposed to high levels of construction dust in the same age range in which to demonstrate if the FEV for construction workers exposed to dust is different than the general male population. Using the data set pulmonary function .sav, blah, 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 or Excel, your null hypothesis. Which is our null hypothesis? Well, our null hypothesis is the mean for all males is equal to the mean for construction workers. There's no difference in the expiratory volume for the two of them. Our alternative hypothesis would be that there is a difference between the two of them, that they're not equal, right? Now, there's other ways to phrase this that are called I don't really want to get into it tonight because we've gone on quite a while already. But this is called two-sided. In other words, we're comparing whether or not construction workers could have higher FEVs or lower FEVs, but just that they're different, just that they're not the same. We're not predicting ahead whether or not they're the same, whether they're less or more, just that they're different. That's why we're saying all males are not equal to uh, 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 all males versus not equal to the mean for male for construction workers, right? We're saying that they're not different. So at any rate, these other kinds of alternative hypotheses are what they call one-sided. This is called two-sided. You go either way. We're not predicting which way it'll go. Often that's the way you probably will work with these kinds of hypotheses. Single-sided hypotheses, like you're predicting ahead of time that it could only be one way, they're easier to prove, they're less rigorous. So that's alone is a good reason to stay away from them. Okay, so using FEV data above, based on the sample size 63, what is a critical value of T you would need to reject the null hypothesis alpha area is equal to 0.05? Okay, so let's see what we have here. I'm going to open up a piece of paper here. Don't save. Okay, let's get rid of the piece of paper. Okay, so my null and alternative hypothesis, if I choose to do that again, it's going to be, let's see, H null, oops, what do I do here? H null, mu for construction workers for all equal to mu for construction workers, or mu for all is not equal to construction workers. Okay, so let's see. So for all males, we know that it's 3.0. So I could just 3.0 here is equal to construction is equal to construction workers. 3.0 is not equal to construction workers. So I take my sample of construction workers, of my 63 construction workers, n equals 63. Okay, you could put this you could have put this the other way. Mu is equal to 3.0, or mu for construction workers is not equal to 3.0, either way. Or you could have just left it mu all versus mu construction workers, and it's understood that it's 3.0. Okay, so based on the sample size 63, what's the critical value of T? Reject the line both says alpha equals 0.05. Okay, and let's see if I got myself a standard deviation here. Look at that. Randomly sampled 16 high levels construction dust, same age range. Look at that. Going to be 3.0. No hypothesis. What value of t? Oh, okay. What value of t would you need to reject the null hypothesis? Well, it actually, for sample size of 63, it's asking you, what would the critical value of t be? Not even asking you to do a calculation yet, is it? So the critical value of t, which I've lost somewhere, or for a critical value of 60 or 63, I'm going to fall back to 60 would be equal to 2.0. That's our critical value t. So you put that in there for that. Using the FEV data, using Excel, enter Excel or calculate the value of t. Okay, so now 12 asks you, this just asks you what the critical value of t was, but didn't ask you to do the calculation, because in this case, we're going to use SPSS to do the calculation. So I'm going to open this file. It's on Blackboard. I have it on my desktop also. I'm going to put away this piece of paper. I'm going to open this file. Remember that critical value of t though, right? 2.0. Let's remember that, because that may come up when we do this. Come on, go away. Doesn't want to go away. Now I'm not going to find it. Let's see. Here's my pulmonary function data.sav. I'm not sure. There's a question there that says C. What is C? Did I say C or something like that? Maybe I said Z. I'm really kind of speedy. Oh, that passed. Look at that. Hopefully it still lets me use it. Open. Data. Desktop. Pulmonary function data. Okay. There it is. Okay, here's my pulmonary function data for those construction workers. Now remember, this is for the construction workers. How many of them are there in this sample? There are 60 of them in this sample. We went back to a sample size of 60. Right? The other question just asked you what the critical value is. We wound up being 60 anyway, because that's what we wound up using off of the t-table. So anyway, here's my 60 construction workers, and I want to compare it to a value of 3. So I'm going to analyze descriptive statistics, and I'm going to go to explore for the hell of it. I'm going to move this in here, and I'm just going to ask it to show me the descriptive statistics, just for the hell of it, just to get an idea of what I'm working with. And let's see, the mean value for the construction workers was 2.83. Oh, okay, lower than 3. Interesting. Maybe we have something here. But can we be sure that it's less than 3? Well, the 95% confidence interval for the true mean, not just the sample mean, is 2.69 to 2.96. Oh, look, it excludes 3. I'm being very encouraged here now. Okay, so let's go and actually do this test, right? I'm going to do our t-test now. I'm actually going to compare them. Okay, I'm going to analyze. Well, let's see. What's a good place to go here? Compare means. And I have a lot of choices in compare means. Compare means one sample t-test. That's where we have a set value like 3 in this case, and we're comparing our sample mean against that set value. That's what we want in this case. I'm going to click on that. I'm going to move my pulmonary function average into test variables, and I'm going to compare it to the value 3.0, which is what we say that is true, the mean for the entire population, the male population. I'm going to click OK. SPSS then goes ahead and does the calculation for us. Let's take a look at that calculation. The mean value was 2.83. We already saw that, didn't we? Sample size was this. Standard deviation, this. Look, even calculated a standard error based on that sample size for us, right? And let's see it when it did the t calculation. The t-value that it got was negative 2.50. 59 degrees of freedom, 60 minus 1, makes sense. The significance, two-tailed. This is the probability of being wrong if we reject our null hypothesis. And so this is really what we want here. That's our t-value, our probability of being wrong, and our degrees of freedom. Let's think about this. The t-score is 2.5. If you remember, the critical value of t for this sample size was 2.0. So we exceeded 2.0. So just that alone, exceeding the critical value of t, says that we can reject our null hypothesis and accept our alternative hypothesis that the mean FEV for construction workers is different than for all males, right? So we could just alone on that, we could do this. But SPSS goes a bit further, and it tells us that the significance, right, with both sides accounted for, possibility of it being lower, possibility of it being higher, is 0.015. That's the probability that we would be wrong if we reject our null hypothesis. So we want this to be less than what value? You guys tell me, what value do we want this to be less than if we want to reject our null hypothesis? 0.05, 5%, exactly right. Okay, so since the probability that we would be wrong if we reject our null hypothesis is less than 5%, we reject our null hypothesis and accept our alternative hypothesis that there is a difference between these two populations. Okay, we could have done it based on the critical value of t, but we certainly could do it based on the significance value, the p-value. Probability is also called the p-value or probability of being wrong. And we need that to be less than our alpha, our acceptable level of error, which we usually set at around 5%. Okay, so basically, I hope we beat this to death well enough that it makes some sense for you. Okay, so I'll leave you guys to go back and maybe redo the homework again if you want to, and so on and so forth. We'll be moving on. The syllabus calls for us to be moving on Tuesday to not just single sample t-tests, but multiple sample t-tests. In other words, comparing two samples, not one sample versus one sample versus a population mean, a given number, like we're doing now, but actually comparing two groups. And it works exactly the same way. The only confusing part is what you're going to choose for the standard deviation, since you have two groups. Do you use the standard deviation of group A? Do you use the standard deviation of group B? Or maybe there was some way you can combine them. So that's the only thing that really complicates that a little bit. We'll talk about how we deal with that going forward.